Hi, and welcome back to our module on weathering. I'm Matt Ross at CSU, and today we're going to be talking about soil weathering. The goals for today's video are for you to be able to describe soil weathering sequences, describe characteristics of soils along a weathering sequence, and describe relationships between soil fertility and solute flux. So this is what you might see in a pedology class or a soil science class, sort of a diagram of a soil, where at the top you have the O horizon, which is sort of rich in organics. The A horizon is right below it, rich in a mix of organics and clays. Then you have the B horizon, which is sort of partially weathered material and some roots. And then you have the C horizon, which is really the interface between the parent material and the soil. And today we're going to sort of focus our discussion on what are the processes that form these soil profiles and what do they tell us about soil fertility and aqueous chemistry downstream. I'm just going to grab the laser pointer. So the question here is sort of how are soils born? And, in our previous lectures by Nick, we really had a lot of discussion about these dissolved ions, so the potassium and hydroxide ions that leach out, that are weathered out of something like a feldspar. But today we're going to focus our discussion really on the kaolinite clays or the soil minerals that are left behind after weathering. And we're going to focus this discussion on sort of the really focused chemical area, but also really broadly on what are the broadest possible controls on soil weathering. And to discuss soil weathering, we really have to go back to one of the grandfathers of the field, Hans Jenny, who sort of came up with this idea of soil forming factors, which are basically just five factors that control soil formation and what soils you'll find in what places. And these can be summarized as CLORPT, which stands for climate, organisms, so what vegetation cover is there, relief or the topography, the parent material, and time. So how long has it been since this started weathering? And this is really a key idea in soil science and soil weathering and understanding chemical weathering in general. So soils develop in predictable ways depending on Jenny's five forming factors: climate, organisms, relief, parent material, and time. And we really know this because we've done a bunch of studies on long-term evolution of soils. And so these studies are often done on what are called chronosequences. This is a famous chronosequence in Hawaii. And basically what you are using a chronosequence for is because it's a common experimental design when you want to explore something that's changing over a really long time scale, but you don't have a million years to wait around. So you change space for time. And so basically these are sites that vary in age all along Hawaii, from 100-year-old sites to million-year-old sites, depending where you are. As you go sort of from southeast to northwest, the islands get progressively older, and so you can sort of see things change over time. There's also precipitation gradients throughout Hawaii, so you can look at dry and wet places. So this gives you a really good area to explore Hans Jenny's forming factors and how they control different soil formation and chemical weathering rates. So this is used to understand the evolution of soils and chemical weathering and plant nutrient interactions. And today we're really going to focus on the sort of soil formation side and one of the major study sequences in Hawaii. And like I said, it captures a lot of that variation in CLORPT. So we'll just take a look here at some data from the Hawaiian chronosequence. This is from Oliver Chadwick et al. In 1999. And I'm just going to focus on some nutrients and some in cations here. We won't talk about the foliar, which is how much is in the leaf. We'll focus on these top two graphs. So on the y-axis, you have soil exchange cations, either magnesium or calcium. And then on the x-axis, you have time on a log scale. And so what we can see is that at the sort of early stage of the chronosequence, we sort of have a low concentration of magnesium and calcium. Then they start to weather out, probably with the addition of plants here. This probably is covered in less plants as you at a really young substrate age. And then you have a lot more plants, and so your weathering rates sort of go up. But then you start to weather out those cations, magnesium and calcium, and you go to lower and lower concentrations along the chronosequence. For nitrogen and phosphorus, we have a sort of different relationship. So nitrogen starts out really low because there's not much in the soil to start with, but then plants start to fix nitrogen, and then you reach a sort of high level of nitrogen that is maintained. Whereas with phosphorus, there's a low level to start, so it's sort of locked up in the bedrock, and then plants start to weather that out with the carbon pump that Nick talked about for chemical weathering, and you start to get higher and higher concentrations of phosphorus in the soil, but then that crashes because essentially you've leached out all the phosphorus available to you, and phosphorus is only available in sort of a mineral form, so you can't pull it out of the air like you can with nitrogen. And so we can sort of think about this as a weathering rate, and so we can see that the weathering rates of phosphorus and calcium on this bottom left graph, they start out relatively high because there's a lot of phosphorus and calcium in the bedrock, but as you leach those minerals out, you start to get lower and lower weathering rates because there's just not much left to weather out. And again, this sort of gives us a snapshot of what's been happening in these older landscapes for a long time, and so can help us understand variation in the chemistry of these places without actually having to watch them change for a million years. And this will just sort of a quick note on the sort of fertility of these soils. As you've leached out all your phosphorus, as your phosphorus sort of weathering rate has sort of gone from relatively high to relatively low because there's none left, now the plants that still need phosphorus, at the beginning, almost all of that came from the bedrock. But as you age out the weathering profile, you have more and more phosphorus contribution from the atmosphere. And I already said there's no gaseous form of phosphorus. So in the case of atmospheric deposition here, we really mean dust. So small particles of dust that are transporting phosphorus across vast distances. And that's now the sort of 90% of the phosphorus in Kauai, which is the oldest island, is basically all from dust, and that's what's maintaining the entirety of the ecosystem there in one way or the other, which is pretty interesting. You can also think about chronosequences as a soil depth profile, where basically at the bottom would be the youngest soil formation, because here we still have a lot of parent material, a lot of cations and phosphorus and nutrients are still locked up in the bedrock, whereas up here a lot of those nutrients have been now locked up in the plants and or leached out. So you'll have sort of like the bulk material will have leached out more of the cations that sort of we talked about in the last slide, but this is just now thinking about it at depth versus thinking about it over like a Hawaiian chronosequence. And sometimes when we think about these weathering reactions, we think about them taking, millions of years like the Hawaiian chronosequence, but they can actually happen quite a bit faster. So this is data from the Mount St. Helens eruption, basically looking at ash and tephra from the Mount St. Helens eruption and looking at the sort of leaching of magnesium, potassium, and sodium out of that sort of ash plume once it had settled nearby. So they basically measured magnesium, potassium, and sodium as it leached out, and basically you can see that over 4 years you started with a relatively high concentration of these elements, and it was quickly leached out. So chemical weathering was really happening here in a 4-year timescale that really dramatically changed the sort of chemistry of this parent material and therefore of the soil nearby. So the key idea here is that soils are really just the last thing remaining. So they're the least soluble materials remaining after chemical weathering and erosion remove all the other elements. So they're sort of the thing that's left behind. And like we had already focused on this. Basically, we can think about this as weathering out a granite, like a potassium feldspar. Previous lectures focused on what was leached out. And then now we can really discuss what is the sort of chemical structure of the things left behind. So this is sort of primary weathering of a potassium feldspar to a kaolinite. And when we sort of look at the physical structure of kaolinite, it can tell us a lot about the soil fertility and sort of how it's going to behave in the environment. And so this is just sort of the class of clays that is called aluminosilicates, because aluminum and silica are the dominant elements that form these clays. And basically the way they behave in the environment is really dependent on their structure. So kaolinite, which is here, is sort of characterized by what's called a 1-to-1 clay. So it has these, for every sort of sheet that you see here on the bottom of aluminosilicates, there's one that is perfectly matched to it. And the bond between those two sheets is really tightly bound. So these are electrically neutral. So they have no cation exchange capacity. They can't hold on to sort of free calcium or magnesium floating around in the soil. And they also are tightly bound enough that water can't enter into them. So these are really unreactive to adding water, which is really different from some other clays we'll talk about. And because you have these perfectly matched one-to-one sheets, these are called one-to-one clays. And they have sort of this features of being electrically neutral and non-reactive to water, so they don't hydrate very well. And they can be the first stage of primary weathering, but they can also be the second stage of weathering. So you could weather to a montmorillonite, which we'll talk about next, and then you could weather that out to a kaolinite. And the features of kaolinite are sort of controlled by its structure, and it forms these really stable layers of aluminosilicates. And that's really in contrast to the next one we'll talk about, which is smectites. This is an example of montmorillonite. And these are what are called 2-to-1 clays, and that's because they have a tetrahedral layer, one octahedral layer, and then one tetrahedral layer. And we don't really have to talk about the specifics of that, but the electrical charge that's generated from this 2-to-1 clay allows for water to enter here, and it also allows for a high cation exchange. So these can hold on to free calcium, magnesium, and other positively charged ions in the soil quite well. This is just the generic formula for a montmorillonite. There's a lot of substitution that can happen because, like I said, they can hold on to positively charged ions. These are, again, called 2-to-1 clays. They're negatively charged. They're highly susceptible to hydration. And they can be called shrink-swell clays, which you'll see in the next slide. So this is a shrink-swell clay on the left here. So that's a 2-to-1 clay, where basically if you add a bunch of water, it'll really swell up. And then if you dry that water out completely, it'll really dry down. This can have major impacts on people who live in Texas, for example, where if they go through a really big drought period, then the foundation of their houses can start to crack because it's shrinking after drying out so much. Where in contrast to that, kaolinite is perfect for making porcelain because it basically doesn't shift its form at all at any level of hydration or heat. So it's really stable at really high heats. And the way these minerals form is basically through a process of desilication. So you have progressively less and less silica in each of these different clays. So starting with montmorillonite, this is again the Hawaiian chronosequence, and what this graph is showing is that as you have higher rainfall, which here rainfall codes directly for weathering rates. So as you have higher weathering rates or higher rainfall, the first thing you form is montmorillonite. So you have a higher amount of silica in a montmorillonite. Then more of that silica gets leached out with more rain or more weathering. And so then you form kaolinite, and then all of the remaining silica from the kaolinite gets removed, and you're left with gibbsite or all these different bauxites that have no silica in them. They're just aluminum oxides or iron oxides. And so as you sort of leach out your silica or your calcium, you're left behind. The soil that's left behind is usually going to be aluminum and iron rich because those don't, they're not soluble. And so they're just sort of the ones that get stuck behind. We can see this just by looking at the ratio of silica to aluminum in some of these clays. So montmorillonite has a ratio of silica to aluminum of 2-to-1. Kaolinite has a ratio of 1-to-1. And then gibbsite has a ratio of 0 because there's no silica left. We can also look at the actual reaction of kaolinite on the left here that I'm circling to gibbsite on the right here. And basically you just see that in this reaction, this dissolution reaction, silica just gets ripped out of the kaolinite and it is weathered away, and you're left with just the gibbsite as the solid form. And, this weathering process leaves behind aluminum and iron hydroxides. And aluminum and iron hydroxides create these nice, beautiful red soils that are really common in tropics because the tropics are warm, fast weathering. They have a lot of rainfall, which also codes for fast weathering, and they have really high vegetation cover, which also can increase weathering rates. And so when you have really high weathering rates, the soil that gets left behind has very little silica, very little nutrients. It's really nutrient poor, which is why in tropical areas like slash and burn agriculture is such a short-lived success because these soils can't hold on to any nutrients left. anymore. They really can't hold on to them in the same way that a like glacial till soil could, that has a high amount of smectite or something. So key idea here is that soil and chemical weathering eventually leaves aluminum and iron hydroxides and iron oxides and hydroxides as the last minerals standing. And this sort of interaction between the conditions that are best for plant growth, which is like a relatively stable high temperature and a relatively stable high amount of precip, are actually the same ones that are that encourage the highest weights of chemical weathering. And so those soils that are older tropical soils, like in the Amazon, they basically become completely denuded or low in nutrients like phosphorus, which have only a mineral component. And so there's this interesting case where we have the highest rates of plant growth, we actually have some of the lowest nutrient soils. And those soils are maintained, the reason we can continue to grow trees in the Amazon, by really interesting ecological phenomena called teleconnections. And so this is just an image from NASA showing that there's these huge dust clouds from the Sahara that get pushed all the way over to the Amazon. And basically, once they reach the Amazon, the plants there take advantage of the fact that this dust is relatively phosphorus rich, because in the Sahara, where there's no water, the weathering rates are basically zero. And so there's a lot of phosphorus in these mineral dusts, and that sort of maintains productivity in the Amazon. So really, this idea is that there's sort of like an inverse relationship between solute flux and soil fertility. So if you have a really high rate of solute flux leaving weathering out your parent material, you're going to end up with a soil that's not very fertile because it's not holding on to any of that stuff. It's all getting fluxed away. And so that's sort of this idea, and I think these teleconnections from the Sahara Desert really feeding the Amazon really highlights that. So that's it for today's lecture on soil weathering. Here's our media credits. See you next time for some redox. No.